In this presentation, I'll be explaining the working of buck converter, the design of the filter inductance and capacitance, and a problem based on the design, and the closed loop application of buck converter. Now let us see the switched mode DC to DC converter. Let us see a circuit shown here. The input voltage equal to VD, and here a load resistor is connected. A switch is connected in series to it, and the output is measured, output voltage is measured across the resistor. Very simple circuit in which when switch is on, the voltage across the resistor will be getting the same as the input voltage VD, and that is during the on period. And when the switch is off, that is during that off period, the voltage across the load will be same as the zero voltage, or the output voltage equal to 0. Therefore, this is the output voltage across the resistor, and this is the on period, and this is the off period, and this is the total time period Ts. And the average value of this voltage can be calculated. It can be calculated like average voltage equal to 1 by the time period Ts integral 0 to T on this voltage Vd into dt. Therefore, that is Vd into T on divided by Ts, or T on by Ts we call it as duty cycle. Therefore, the average output voltage equal to the duty cycle into the input voltage. Therefore, by changing the duty cycle, we can vary the average output voltage. Therefore, that is a basic concept of a DC to DC converter, a step-down converter. Now, what are the issues here? Now, here the one issue is that in practical circuit, the load will be having an inductance. This load will be having an inductance, or even for a resistive circuit also, it will be having the it will be stray inductance will be there. Now, because of the inductance of the load, then leading to a dissipation, or that will be producing a voltage that will be coming across. That is, when switch is off suddenly, because of the inductance, a voltage will be developed across the switch that will be destroying the switch. Therefore, that is because of the inductance of the load. That's the one issue. Second issue is that output voltage is, in this case, in this circuit, the output voltage is not constant. It will be either Vd or 0. Therefore, these are the two issues of this particular circuit. And if you, in order to, rectify, or in order to rectify this, the drawbacks, or there's a modification of the circuit is done, in which what we have done is that a diode is connected across the load. A freewheeling diode is being connected. Therefore, when connecting a freewheeling diode, then there will be a circulation of energy in that circuit that will be protect the switch. That's the first modification. Second modification is that since we are getting either VD or 0 voltage, we want to get the average voltage. We want to use a low pass filter at the output side. Therefore, if you include these two things, this circuit will become next. Then it will be a buck converter. Now let us see that one in the next slide. That is modification of this very simple circuit. How to form to a buck converter by introducing a freewheeling diode. That is to protect the switch. Second, by introducing a low pass filter in order to get the average DC output voltage. Now coming to the buck converter or step down converter, after those modifications what I explained in the last slide, one thing is that we are adding a freewheeling diode in series to the switch. That's the first stage. Second change that we are introducing a low pass filter, LC filter, between the load and the switch as such. Therefore, this is a low pass filter, and this is the diode that we are added. And then this particular circuit we call it as buck converter. So the problem of the stored inductive energy is this overcome by connecting a freewheeling diode, and the output voltage fluctuations are much diminished by using a low pass filter, LC filter. Therefore, thus we'll be getting a constant output voltage like this one. Of course, there's a slight ripple is there, and very, very less compared to the average output voltage. Therefore, that is obtained by this LC filter. And the switch is being protected by, because of the inductive energy will be circulating to the freewheeling diode. Therefore, the switch is being protected. Therefore, that is the modification of the previous circuit. That then this particular circuit we call it as buck converter or a step down converter. And as we already seen, the average output voltage is equal to the average value of this voltage. Average value of the voltage is given by, that is this capital V0 is the average voltage, which can be calculated by 1 by the switching period Ts integral 0 to T on Vd dt, or it is equal to Vd into T on by Ts, or D into Vd, or D is called the duty cycle, which is the ratio of the on period to the total time period. By changing the duty ratio, we can vary the average output voltage that is available across the load. That is the basic concept of the relation between output voltage and input voltage of a buck converter. Therefore, this is a buck converter circuit, and this is the output voltage with a small ripple is there, that is called delta VC. Now, if you see the filter design, coming to the filter design, because this is the output voltage that is available at the this is the voltage that is available across this one, V0I. Across the diode, this is the voltage, and that is given as an input to the filter. Therefore, if you do the Fourier analysis, that contains the DC component, that is capital V0, that is this voltage. Apart from that, there are harmonics are there. That is, I mean, at the switching frequency, 2 times the switching frequency, 3 times switching frequency. These are the harmonics. But what we want to across the load is only the DC component. We want to eliminate these frequency component. For that one, we'll be designing a low pass filter to reject these frequencies, so that here at the output we'll be getting only the DC component, which is equal to the average value of this voltage, which is equal to D times the input voltage. Therefore, this is the frequency response of this voltage that is available across the diode, and that is given as the input to the low pass filter, and output of the low pass filter you'll be getting a constant DC output voltage, that is V0. And here one more thing we'll be seeing later, the cutoff frequency of this filter we'll be seeing later, that is it is equal to the FC equal to 1 by 2 pi root of LC, where L is the inductance of the filter and C is the capacitance of the low pass filter, and 1 by 2 pi root of LC is the cutoff frequency of this low pass filter. We'll be seeing the design the later coming slides. Now let us see the buck converter or step down circuit states. But we are considering is a continuous conduction mode, CCM. That is in continuous conduction mode, the inductor current never goes to zero. Therefore, the current through the inductor, this is an LC filter at the output of this, and that is connected, and the inductor current never goes to zero in continuous conduction mode. For what we are considering here is a continuous conduction mode in which the inductor current never goes to zero. Now coming to the different states of switch, the switch can be either switch on or off. There are two states are there. The corresponding equivalent circuit, when switch is on, we can see that one when this is the input voltage plus VD, and when switch is on here, this diode is getting reverse biased. Since the diode is getting reverse biased, this circuit is now becomes this one. Therefore, there will be an inductor and filter inductor and low pass filter inductor and capacitor across that switch, across that load resistance comes. Therefore, this buck converter reduces to this form when switch is on, since the diode is reverse biased. And the corresponding voltage across the inductor can be found out by using the Kirchhoff's voltage equation corresponding to this one. And from that KVL equation, when switch is on here, the voltage across the inductor, that is, this is the input voltage equal to VD, average output voltage equal to V0. Therefore, this voltage across the inductor is given by VD minus V0. That is as per the Kirchhoff's voltage law, the voltage across the inductor equal to VD minus V0. Therefore, that is the voltage across the inductor shown here when switch is on. When switch is off here, because of the energy stored in the inductor, this is since the current is flowing in the same direction, here plus and here minus, or here the diode is getting forward bias, freewheeling diode is getting forward bias, then the circuit is moving to this. This is the state of that one. This is the equivalent circuit when switch is off here. Again, we are applying the Kirchhoff's voltage law to this equation, since we are neglecting the drop across the diode, almost zero voltage here, and this output voltage is same as the previous average output voltage is not changing, V0 here, and this voltage equal to VL. Again, if you apply the Kirchhoff's voltage law to this loop, plus VL or VL plus V0 equal to 0, or VL equal to minus V0. Therefore, when the switch is off, the voltage across the inductor equal to minus V0, and when switch is on, the voltage across the inductor equal to VL minus, VD minus V0, input voltage minus output voltage. Therefore, this is a positive voltage that is coming across the inductor, and this is a negative voltage that is coming across the inductor during off period. This is during on period. And if you plot the current through the inductor, as you know that the basic relation is VL equal to LdI by dt. Since since during this period, 0 to on period, the voltage across the inductor equal to positive, the DIL by dt is positive. Therefore, the current through the inductor is building up. And once the current voltage across the inductor goes negative, once it is switched off here, VL equal to LdI by dt, VL is negative, therefore di by dt or DIL by dt goes negative, that is the current is decaying with a negative slope. And again, one more thing is that this current is same as this current. In continuous conduction mode, IL at 0 is same as IL at TS. Therefore, since under steady state current, this current is same as this current. And this one is called, this is called the average output current I0, same as the low, the inductor current. And this is this ripple current we'll see in the coming slides while designing. Therefore, this is the buck converter circuit. Same circuit is here. Switch is there. There is a feedback or freewheeling diode is there. And there's an inductor, low pass filter. This is actually low pass filter that to extract the DC component or to reject all the other frequency component. That's the purpose of LC filter. And here we'll be getting the average output voltage or DC component of the voltage that is coming across the freewheeling diode that is extracted by this LC low pass filter. Now let us see the inductor voltage across the inductor as well as volt second balance concept of a buck converter. Buck converter, what do you mean by this is applicable to all the converters, volt second balance concept. And what is the inductor voltage also we are considering for a buck converter here. Therefore, in a buck converter, as we have seen, when switch is on, the voltage across the inductor equal to Vd minus V0, a positive voltage coming across the inductor. When switch is off, the voltage across the inductor is, this is equal to 0, or this diode is conducting, this voltage 0. Therefore, this voltage is equal to minus V0, or minus V0 is the voltage across the inductor. Therefore, the voltage across the inductor is plotted, and during this period, the voltage equal to Vd minus V0, and when switch is off, the voltage across the inductor equal to minus V0. Therefore, this is the inductor voltage. As I already explained in the previous slide, the current through the inductor and the voltage across the inductor is related by VLT equal to L DIL by dt. Therefore, during the on period, as you know that the voltage across the inductor equal to Vd minus V0, or that is equal to L DIL by dt, or the rate of change of current through the inductor with respect to time equal to Vd minus V0 divided by L. Since Vd minus V0 equal to positive, the DIL by dt or di that is equal to positive. That is why current through the inductor is building up with a positive slope. And the slope is given by Vd minus V0 divided by L. And when switch is off here, the voltage across the inductor is equal to minus V0, minus average output voltage V0. And here, similarly, we are substituting here minus V0 equal to L DILT divided by dt, or the current through the rate of change of current through the inductor with respect to time is given by minus V0 divided by L. Since there's a negative voltage, the slope is negative, that is, for current is decaying and that is reaching at this point, that is, this is the total time period Ts, and this is the on period and this is the off period. When again, once it reaches the time Ts here, again, that is same as this current I at 0. So this is decaying and then that is repeating. Therefore, this is for a continuous conduction mode in which this is the positive slope and the current to the inductor is positive and this is the negative decay. Therefore, that is equal to minus V0 by L, and the positive slope is given by Vd minus V0 divided by L. In any switching converter, under steady state, the net change in the inductor current over one switching period must be 0, meaning that over one switching period, the initial current is equal to IL at 0, same as IL at Ts. Therefore, these two currents are equal. Under steady state condition, the initial and final values of the inductor current are equal, meaning that IL at Ts, that is the current inductor current at Ts is a switching time period, and equal to IL at 0. For under steady state condition, ILTS equal to IL0. Now again coming back to the voltage across the inductor, VLT is equal to LDIL by dt. Already we know that equation. Or from this equation, if you calculate the current IL at Ts, or we can see that one, it is equal to, from this equation, IL at Ts, we have to see IL at Ts equal to 1 by L integral 0 to Ts VL dt. We are integrating this one, that is integral VL dt plus the initial value of the current. That is as per the equation, that is IL at Ts equal to this one. Or from this equation, IL at Ts minus IL at 0 equal to 1 by L integral 0 to Ts into VL dt. Or from here, you know that inductor current at 0 is same as the inductor current at Ts. Since these are same here, equal, IL Ts minus IL0 equal to 0 here. we will be getting 1 by L integral 0 to Ts VL T dt equal to 0, or 1 by L integral 0 to Ts VL dt equals 0. That means that integral 0 to Ts VLT dt equals 0, or meaning average voltage across the inductor over one switching period equal to 0. Therefore, the average of this voltage across the inductor on this one switching period is equal to 0, meaning that if you take the average, positive area should be equal to negative area. Only that's a condition. And for a volt second balance means that average voltage across the inductor equal to 0. Otherwise, what happens is that if there's a net, volt second is there, meaning that net flux will be developing. Or since the product of voltage and second means the flux, actually the unit is flux. Therefore, if there is a net volt second, or if there is a net area is there, there will be net flux will be there. Therefore, as it proceeds here, that core will get saturated. Therefore, after one switching period, the net flux, change in flux should be equal to 0, meaning that this positive area should be equal to negative area. That's called the volt second. This area is nothing but the product of voltage and time. That's called volt second. Therefore, average voltage across the inductor over one switching period equals 0 means volt second, or the positive area should be equal to negative area. The net area over one switching cycle should be equal to 0. Otherwise, the core gets saturated because there will be a change in flux that causes to the saturation of the core. Therefore, the volt second balance should be obeyed in a inductance circuit of any converter. Now, continuing the volt second balance of buck converter, thus under steady state condition, the integral of the inductor voltage over one switching period must be equal to 0, or integral, that's the unit of volt second, means nothing but voltage into time. It is a flux linkage. Therefore, the net flux linkage over one switching period should be equal to 0. Therefore, net change in flux should be equal to 0. Otherwise, the core gets saturated. Therefore, in order to make that 1 by L integral 0 to Ts VLT dt should be equal to 0. Integral 0 to Ts VLT dt should be equal to 0. Or above equation says that the total area, that as I told you in the previous slide, total area should be equal to 0. Therefore, positive area, the total area or the volt seconds under VLT performance equal to 0. That is, positive area should be equal to negative area. Or we can see that one integral 0 to Ts, which is equal to 0 to T on VL dt, that is this area. And from T on to Ts VL dt, or this area, therefore the sum of this area should be equal to 0, or meaning that this area is nothing but this is equal to Vd minus V0, and this is equal to T on. Vd minus V0 into T on plus this is equal to minus V0 into Ts minus T on. That is, this is equal to T off, which is equal to Ts minus T on. That should be equal to 0. Or from this equation we get that Vd into T on, reducing this one, Vd into T on equal to V0 into Ts, or V0 by Vd equal to T on by Ts, which is equal to the duty cycle D. So that is the relation between the output voltage, average output voltage of the buck converter, and the input voltage. That is V0 divided by Vd equal to D, which is equal to duty ratio. And here in continuous conduction mode in CCM, neglecting the power losses associated with all the circuit elements, that is neglecting the power loss of the switch, diode, etc., or inductor, or capacitor, like that associate elements, then you can see that input power is the same as the output power. Therefore, input power is given by input voltage Vd into the average input current equal to Id, which is equal to the average output voltage equal to V0 and the average output current to the load equal to I0. Therefore, V0 into I0 equal to Vd into Id, neglecting all the losses, or the output power equal to the input power, or Vd into Id equal to V0 into I0, or we can say that one I0 divided by Id, which is equal to Vd by V0, which is equal to 1 by D. Therefore, output current, average output current divided by the average input current equal to 1 by D, and output voltage, average output voltage divided by the input voltage equal to D. This is something analogous to, or it is similar to a what is called a step down transformer. That is, hence in continuous conduction mode, step down converter or a buck converter is an equivalent to a DC transform. It is equivalent to a DC transformer. Just like, is equivalent as such. It's a step down mechanism, because just like as in a AC transformers, we can see that output voltage divided by input voltage, secondary output voltage to the primary voltage equal to N2 by N1, and I2 by I1 equal to N1 by N2 like that. Similar to that one, in this one, it can be analogous only DC transformer like it is equal to the output voltage divided by the input voltage is equal to the duty ratio D, sorry, duty cycle D, and the output current, average output current divided by average input current is equal to 1 by D, where D is called the duty cycle. I0 is the average output current and ID is the average input current. Therefore, that is the concept of volt second balance. Now let us see the design of a buck converter. That is design of buck converter in the sense, one thing is that basically that we are designing the filter value. What should be the value of the inductance and what should be the value of the capacitor. Therefore, the low pass filter inductance and low pass filter inductance will be dealing here, and the next slide we'll be seeing what is the low pass capacitor also will be designed. Therefore, this is the buck converter, but we already discussed. Switch is the freewheeling diode is the low pass filter inductance and capacitance, and this is the load. And the average, input voltage equal to VD and average output voltage equal to V0. And here, during the T-on period, as we have seen when switch is on here, we have seen the average voltage across the inductor is given by VD minus V0. Or the corresponding equation L di by dt equal to L into the change in current is changing from I1 to I2. Therefore, the delta is given by I2 minus I1. Therefore, I2 minus I1 divided by the time period equal to on period. Therefore, divide by on period, or L into this I2 minus I1 I am representing as delta IL. L into delta IL divided by the on period. That is the voltage across the we are seeing that is equal to the voltage across the inductor when on. And or from this equation, we can see that this is equal to VD minus V0 equal to L DIL by T on. Or from this equation, we can see that the change in current, inductor current, that is I2 minus I1, which is equal to VD minus V0 into T on divided by L. From this one, we'll be getting the delta IL equation when switch is on. Or delta IL equal to VD minus V0 divided T on divided by L. Or here VD minus, V0 is already we derived D into VD. For VD minus D into VD into T on equal to D times the total time period TS, DTS divided by L. Substituting this one, VD can be taken outside. Therefore, we will be getting D into VD into 1 minus D divided by, of course, the TS I can write as 1 by Fs into L. So this is the equation for the change in current delta IL. The change in current, that is I2 minus I1. This is the delta IL that is given by D into VD into 1 minus D divided by Fs into L. Fs equal to 1 by Ts. Therefore, this is the delta IL. Or from this equation, you can find out what is the the inductance value. Normally in the problem, we'll be giving what is the permissible value of the delta L, or that how much change in inductance is permitted. That is delta L will be given. Therefore, then you will can calculate what is the inductance value required is given by D into 1 minus D into the input voltage VD divided by the switching frequency Fs into the permitted value of the change in inductance current, or delta IL. Therefore, thus we can find out what is the value of the inductance. Therefore, where delta IL equal to I2 minus I1. Therefore, this is the this is the voltage across the inductor VD minus V0 and minus V0, and of course the corresponding current, inductor current is shown here. This is the inductor current, and this is the average value of the inductor current, which is same as the average value of the load output current I0. Therefore, I2 minus I1, that is equal to delta IL, and this is the, we'll see what is the capacitor current. Capacitor current, the change in capacitor current will be same as the change in inductor current. We'll be seeing the coming slide. Therefore, this is the relation to find out what the inductance or the low pass filter inductance can be calculated if you know delta L, which is equal to D into VD into 1 minus D divided by Fs into delta L. Now coming to the design of the capacitor, that is filter capacitor. Normally to design the capacitor, we'll be giving the permitted value of voltage, change in voltage of capacitor, or delta Vc will be given. To design inductor, we have seen delta IL will be given. To design C, delta Vc will be given. Now this is the same circuit here, and as we have seen, this is the inductor current changing from I1 to I2 during the on period. again during the off period, it's again changing to I2 to I1. Therefore, this is the, in continuous conduction mode, this is the inductor current waveform. And as we have seen here, if you see the total inductor current is same as the summation of the capacitor current and the load current. Or if you see that one, since we are assuming the constant load current, the change in inductor current will be same as the change in capacitor current, because we are assuming the load current constant. Therefore, the change in inductor current is same as the change in capacitor current. Therefore, this is the change in inductor current what we are shown from this one. That will be same as this capacitor current. It is the changing, because if you take a middle of that one, if you plot that one, this is the capacitor current, or change in capacitor current is same as the change in inductor current. And because of this change in capacitor current here, that will be storing a charge in the capacitor. This is the capacitor current waveform here, and that will be storing a charge in the, and in order to plot that one, it is plotted, that is the current versus time is plotted. The product of current and time is equal to charge. Therefore here, and this is the output voltage waveform of the across the load. This is the average output voltage, and this is the ripple as such. So this ripple voltage is coming the voltage across the capacitor. That is, this is the ripple voltage that is coming across the capacitor, same as the output voltage, and this is the average output voltage. And because of the ripple in output voltage, that is called delta VC here, that in order to find, there is, we can see that one, here the capacitance current or the capacitor current is here, it is linearly changing like the positive slope here, because here the capacitor voltage, and here this is the of course this is the capacitor's current as such. Therefore, this is the capacitor current and the charging and discharging, and the product of capacitor current and time, that this area, this represents the charge as such, or this is the delta Q. Therefore, the change in voltage of this change in capacitor voltage is because of this charge that is shown here, delta Q. This delta VC is because of this charge shown as the shaded portion. So this is the delta Q. And this duration is nothing but, we are approximating that duration is the half of the time period. So Ts by 2 is this duration, and the charge stored in this duration, because of this charge, there will be the change in voltage from here, of course, from this to this, or the change in voltage delta VC is causing because of the charge, that is delta Q. Therefore, coming to here, delta IL is same as the delta VC, because the load current is assumed to be constant. So whatever the change in load current is reflected in the change in capacitor current, because we are assuming the load current equal to constant. Therefore, from this triangle here, we can calculate what is this area, that is called the delta Q, which is equal to delta VC, this delta Q. Therefore, delta VC, or the change in voltage, is equal to delta Q because of the Q by C, or delta Q by C. Or delta Q is equal to, you have to find out this area, half BH, half into B is equal to TS by 2, H is equal to, we have to find out what is H means, total height is equal to delta IL. For half of that, which is same as delta IC, same as delta IA, for the half of that one is taken. For delta IL by 2, that is the H, half BH. For that's the total area here. Therefore, that is, this total area means represents the change in charge. Because of this delta Q only, there is a change of voltage delta VC. Therefore, that divided by the capacitance, that is the change in voltage, capacitor voltage, that is available at the output. Delta VC is equal to, then that can be reduced as, it is equal to, from this one, delta IL divided by 8 into Fs into C, substituting here, or we substitute for delta IL, which is already calculated in the previous slide, which is equal to, then we'll be getting D into 1 minus D into Vd divided by 8 Lc into Fs square. Therefore, this is the equation for the change in capacitor voltage, this delta Vc. Therefore, that Vc calculated, from this one you can calculate what is the value of the capacitance required, equal to D into 1 minus D into Vd divided by 8L Fs square into delta Vc. Therefore, normally in the problem, the permitted value of the capacitor ripple or delta VC will be given. From that one, from this equation, you can find out what is the value of the capacitance required to limit the voltage ripple to this value. Therefore, this is the equation to calculate the filter capacitance. And after calculating the capacitance, filter capacitance and filter inductance, there is a cross-checking is there. That is, Normally, this is a LC filter. What is the corner frequency of the LC filter? Which is equal to 1 by 2 pi root of LC. In that problem, we'll be seeing the next one. In that one, we'll be seeing it is equal to, the condition is that the cutoff frequency should be much smaller than the switching frequency. That is the one condition to be satisfied. After finding out L and C, you have to cross check that one. 1 by 2 pi root of LC, that is the corner frequency of the LC filter, that should be much smaller than the switching frequency of this, switch. That is the condition to be satisfied. Therefore, this is the method how we can design the low pass filter inductance as well as capacitance. Now coming to a problem of buck converter. A buck converter has an input voltage of 14 volts. The required output average voltage equals 6 volts. And peak to peak, the current ripple, inductor current ripple is given by 15 millivolt. And this capacitor voltage, not the inductor. Inductor is the current only. The current limit is 0.6 amperes. That is a delta IL equal to 0.6 amperes, and delta VC is given as 15 millivolt. And the switching frequency is 30 kilohertz. And if the peak to peak ripple current is 0.6, determine the duty cycle and the inductance value as well as the capacitance value. We have to design L and what is the C. First, we have to find out what is the duty cycle. In order to find out the duty cycle, input voltage equal to 14 volts, output voltage is 6 volt. Then you can calculate output voltage equal to D times VD. From that one, duty cycle equal to, V0 divided by VD, 6 divided by 14, 0.428 or 42.8% is the duty cycle of the switch. And the switching frequency is given as 30 kilohertz. And the equation for to find out the inductance as we already seen, which is equal to D into 1 minus P VD divided by F into delta IL. Delta IL is given as 0.6 amperes. Substituting that one in this equation, we can get the inductance to limit the current ripple 0.6 amperes is equal to 190.4 microhenries. And similarly, to calculate the value of the C, we have to take the voltage ripple. Voltage ripple is to be limited to 15 millivolt. Therefore, delta VC should be limited to 15 millivolt. And as we already this equation, C equal to D into 1 minus T into VD divided by 8L into Fs square into delta VC. Substituting in this one, all these values are there. Inductance value is already calculated from this problem, this one. And then you will getting the capacitance value is equal to 166.67 microfarad. Therefore, this is the capacitance value and this is the inductance value and this is the duty ratio. And as I already told you, a cross-checking is to be done. What is the, the cutoff frequency of the low pass filter? This is an LC forms a low pass filter. What is the cutoff frequency? 1 by 2 pi root of LC. Therefore, substituting that one, we will be getting it is equal to 893.42. This is much less than the switching frequency, 30 kilohertz. That is why it is just, correct as, but design is correct. We found out the value of the inductor and the capacitor. The same thing I just simulated and MATLAB, the same circuit as I've already explained. Same circuit, a buck converter with the same value as we had seen in the last problem. And we'll be getting the required output voltage, as the output voltage is 6 volts and input voltage is 14. And we'll be getting a 6 volt with the same value what I designed is taken here and that is simulated. It's a open loop buck converter. It's no closed loop as such. So this is the output voltage 6 volt. And this is the circuit of buck converter that is simulated using MATLAB. This is a source and this is a switch as inductor and the capacitance and the load. And this is a freewheeling diode. So this is the output voltage which we will be getting 6 volts. Now let us see the closed loop control of a buck converter. Buck converter already we have seen. There is the input DC voltage and this is the load. And this is a LC filter, low pass filter. And this is a freewheeling diode and this is a switch. Therefore already we have seen. Now the closed loop control is to make if at all the input voltage is fluctuating or it's varying, that output should not change, or you want to keep, that's called the line regulation. And of course, input voltage variation, the output voltage should be constant. Therefore, for example, here input voltage equal to say 100 and output voltage what we designed is equal to for a 0.5 duty ratio cycle, or output equal to 50. That is the thing closed loop. But if input is suddenly changing from 100 to say 150, if you are keeping the same duty ratio 0.5, output will be moving to 75. Therefore, you always want to keep the output voltage constant. Therefore, for that one, we have to do the closed loop control of buck converter. Therefore, this is the control as a closed loop control, and this is the power circuit, and this is the control circuit as such. For that one, what we are doing is that output is sensed using a voltage sensor is done, and that is compared with the reference voltage. For example, in this case, I want to keep the output voltage to 50. The input voltage will say 100. Therefore, the actual voltage is taken and this reference voltage is taken as a 50 volt. And then error is taken, and this error is given to a PI controller, proportional integral controller is there. And the PI controller output is compared with a sawtooth waveform, triangular sawtooth waveform as such. And as that is output of the, the comparator is given to the switching signal as the MOSFET, it is given as this one. Therefore, that is the circuit diagram. This is the control circuit, and this is the power circuit. This is the inductor, capacitor, low pass filter, and this is the freewheeling diode, and this is the load as such. Now here, let us see the working of that one. Assume that here the input voltage is suddenly changing from 100 voltage to 150. Now, if there is no closed loop control, we can say that at that instant, whenever the voltage is suddenly changing, what happens is that since it is operating at a 0.5 duty ratio, suddenly the output will be shifting to 75. But already the reference voltage what we kept is the 50. Therefore, here equal to minus terminal 75 comes, here 50 comes. Therefore, then error is coming. Error is, when error means here negative is more than, but given to a negative, minus is more than positive. Therefore, a negative output is getting. That is given to a PI controller. And so that the output of the PI controller, what happens is that because of the negative at the input of the PI controller, output of that's the input to the comparator. Here, if you see that one, this is the sawtooth waveform that is given to the comparator, which is given to the negative terminal, and positive terminal you are giving the output of the PI controller. Since it is you are getting a negative voltage when the voltage is suddenly changing to 75, because this is a 50 positive and this negative, and as this is changing to a output is, what happens is that the input to this negative input of the comparator here, that is going down. As this goes down, here this is the controller, that's the output of the PI controller, and that is going down means that here you can see that one going down, that on period gets reduced and off period increases. For when this is more than this one, you will getting a positive, and when this is control is less than this sawtooth one, we will getting negative. Since this voltage is going down, the on period gets reduced and off period increases, meaning that the duty ratio reduces, or then duty ratio reduces, meaning that finally the previously duty ratio was 50%. Finally, this now to get a 50 output with a 150, it will become 50 by 150 or 33.33 or 1/3. 33.33% duty cycle comes. That is by reducing this or by moving this control signal down, the on period reduces and off period increases, so that the duty cycle will become now 2.33 or 33%. That is stabilized to that value, so that you'll be getting the output voltage. Now assume that the input voltage is suddenly reducing from 100 to 75. Then the output voltage, since it was operating at 0.5, suddenly if it is the input voltage is reducing to 75, this voltage is reducing to 37.5. But already the reference voltage we kept it as 50. For 50 minus 37 means, of course, this will be positive. Or when this is positive, the PI controller output is this is a control output that gets increased. As this gets increased here, we are comparing with a sawtooth waveform, since it is given to a positive terminal here. As this increases, the on period increases and off period reduces, or duty cycle increases. As duty cycle increases, finally the duty cycle will be coming to, see here 75 and here 50. 50 by 75 or 2/3 or 0.667 or 66.67. That to that value it will be getting settled down. Therefore, as there is a change in input voltage here, the duty cycle is automatically controlled by this setup using an error is taken, that is given to PI controller, and that is compared with a sawtooth waveform. This output is given to control the switch, so that as there is a change in input voltage, the duty cycle is being controlled, so that you'll be getting the output voltage constant as required by the reference. Therefore, that is the way in which the closed loop control of buck converter is implemented. Therefore, these are the this is a sawtooth waveform, and this PI controller output is this one, and this is the output of this comparator that is given to the input to the switch, and the same circuit is shown here also. Therefore, this is the closed loop application or closed loop way in which the buck converter is working. The same thing I simulated, simulated using the MATLAB simulating here closed loop. And the thing is that I have changed the circuit, the input voltage I changed from 14 to 20. There's a perturbation is done at the input side, and here PI controller, I mean error is taken with a reference, it is compared, and here that is, therefore here the input is changed from 14 volt to 20 volt. That is, this is the input perturbation is done at this instant. 14 volt to the 20 volt is done, and this is the output voltage which is set to at a 6 volt is there, and here there's a slight, at this point there's a perturbation is there. Finally, it is settling down again to the um, 6 volt. Therefore, this is the output voltage waveform. This is the input voltage waveform, and when the input is changing from 14 volt to 20 volts, and here we are using a PI controller is using for the reference voltage is taken as 6, and the PI controller is that Kp value is 0.01, and that is by trial and error it is fixed like Kp equal to 0.01, and in integral constant, proportional constant 0.01, and integral constant equal to 1. And this is the closed loop Simulink diagram of the model of the buck converter. Therefore, this is the output waveform, and this is the input voltage perturbation, and this is the output voltage waveform. Therefore, that is the working of a closed loop control of buck converter, in which the input is changing from 14 volt to 20 volt, and the output voltage is constant at 6 volt. Therefore, as there's a transition is coming, this is like overshoot like this one is there, but it finally is settling down to the required reference voltage, that is 6 volt.